A test particle moves along the geodesic of the curved spacetime. That means the particle is under a free-falling motion. However, correction to the small body's geodesic motion will arise due to the spin in which the internal structure couples with the curvature of the background spacetime, modifying its motion. Spinning particle moves according to the Matheson-Papapetrou equation. However, this equation contains some degree of arbitrariness owing to the freedom of choosing a particle's reference frame due to the absence of a unique center of mass in general relativity. An additional condition is imposed to turn this equation into a closed system. These conditions are called the spin supplementary conditions. In this study, we use space-plane analysis to study the behavior of a particle with spin orthogonal to the equatorial plane orbiting a Schwarzschild black hole. We assume that the spin is very small compared to the total angular momentum and consider only its second-order correction to the equation of motion. This method is useful for gaining a qualitative understanding of object dynamics without explicitly solving for the differential equation. We also construct the object's phase portrait, which will determine the particle's possible trajectory, and from that phase portrait we can translate the trajectory into the physical space. We found out at the second-order spin correction, bound orbits still exist for sigma greater than square root of 1 over 6 spin. It would be interesting to apply this method for other spherically symmetric spacetimes.
Despite advancements in cosmology, there are still more that we need to understand in the true nature of dark matter and dark energy. In an attempt to do so, some mathematical models propose an interaction between the two components or express dark energy as a scalar field with a given potential. If we could somehow connect these models to something more familiar, this might provide a more in-depth comprehension on their nature. Thus, we ask ourselves, could the dynamics in our proposed model, when dark matter vanishes, be analogous to some mechanical system? Using the dynamical systems approach, and analyzing the invariant manifold where dark matter vanishes, it turns out that we can find similarities with the behavior of a familiar mechanical system, but only when the Hubble parameter is constant. Such a connection is no longer applicable when the parameter becomes time-varying. We infer this by applying an imagery of a ball rolling in an exponential potential to the sample phase plots of the h equals constant case, where the dynamics of the kinetic and potential energy of the scalar field is analogous to those of the said mechanical system, and also to the plots of the time-varying case, which portray a different scenario altogether due to its non-autonomous nature. To further understand the second case, one can try to find a time-dependent mechanical system that would be analogous to this case.
Good day everyone, I am Kenneth-chan Memoramo together with Dr. Eric A. Calabon, and today I'm going to present our paper entitled Generalized Contour Integral Representation of the Finite Part. So the evaluation of the state resistance form given by equation 1 using the finite part integration for a small parameter omega was successful in covering the missing terms that are missed out in the classical term with integration. Central to this method is a contour integral representation of the finite part in the state resistance form. So in our study, we will obtain a more general expression for these integral representations. So for the case of the closed singularity, we have the following theorem given by equation 2, where Cp is the contour shown in figure 1. On the other hand, for the case of the French cone singularity, we have the following theorem. So now we will apply this contour integral representations in obtaining a climate integration of the incomplete resistance form given the equation for the neighborhood of small omega. So with that, we have the following lemma for the case of the pole singularity, whose contour of integration is shown in figure 2. On the other hand, for the case of the branch point singularity, we have the following lemma. So for the conclusions, using an arbitrarily oriented contour of integration, a generalized contour integral representation of the finite part and the state resistance form that is consistent with the finite part integrations were obtained. The general representations can be used as an alternative. For example, when phi is equals to minus pi, the branch cut corresponds to the principal value and the resulting representations can be used in evaluating integrals to negative real line. This also shows that the contour integral representations of the finite part is not unique in the sense that we can use different contour integrals that will lead to the same finite part.
Black holes, dead things which are extremely fascinating. It is a region in space where gravitational field is so strong even light cannot escape. When a particle orbits around a black hole, it emits radiation which is heavily influenced by the nearby strong gravitational field. One way to characterize this influence is to investigate the radiation's energy as it propagates to a distant observer. This can be done by calculating the energy shift function. This energy shift function quantifies the radiation's energy influenced by the spacetime curvature and the Doppler effect arising from the motion of the emitting particle. This energy shift function is dependent in the particle's motion dictated by the angular velocity and the gamma factor. It is also dependent on the relative angular position of the observer and the emitter. We find that if a distant observer is coplanar with the emitting particle, the energy shift of the radiation takes its extremum values. We also find that the value of the energy shift function approaches zero as the emitting particle approaches the photosphere region. As a sanity check, the energy shift function becomes unity at infinity. This only means that there is no difference between the emitted frequency and the observed frequency at infinity. This study has given us insight on how a black hole affects the energetics of radiation emitted in its vicinity. There are other quantities that we can investigate in order for us to fully quantify the strong gravity effects on radiation emission. We can look at the quantities such as the flux and the trajectory. These quantities will be investigated in the future. Thank you.